Hello, I'm Philip Muggleston, and in this series of videos we're covering the predictive capabilities native to SAP HANA. In this video we're going to look at another flavour of regression. This time it's going to be natural logarithmic regression. This is very similar to what we already saw with geometric regression. Effectively, the curve fit, it follows a log model, so it looks something like this, a natural log curve. So it looks something like that. And in fact, under the covers, what the HANA will do in terms of calculating this is simply to convert this to linear by taking the logs and then work out the values and then convert them back again. So it's another variation, and in some cases the data may well fit this model better than other models. So let's see how we actually make that work with HANA. Natural logarithmic regression is very similar to the geometric and simple linear regression that we've already seen. It's bivariate regression, meaning that we're working on a single explanatory variable, and we're going to have a single dependent variable, which is what's going to actually be predicted. So, as we've seen, we'll work with the same data set, we'll work with the customers that you've already seen. We're going to use income as our explanatory variable and life spend as our forecast or our predicted variable. And the parameters that we put into the PAL library are basically the same as you've already seen. There's really only one little difference here, and that's the actual name of the algorithm. And this time, for natural logarithmic regression, we need to put ln as a prefix to the word regression. That's really the only change. Everything else is pretty much as we've seen in the other examples. So I won't go into detail on that. Let's go and run this. So let's run the code. Creates the signature tables and runs the model. So if we now refresh our list of tables, we can see that we've got, as always, a coefficient table. So we can look at the coefficient. So this is the equation that the values will be substituted in when it does the calculations, to save you doing it yourself. We see the significance table. Again, this has got our R squared value and our F distribution, or our F value. In this case, R squared is 0.68, so it's probably the lowest one we've seen so far. It's not that close to 1. So it may well be that this customer data is not particularly well suited to geometric or natural logarithmic regression. However, it's always worth trying these out to try to see which is the best fit in terms of your input data, so which is the best model you can create. We've got the PMML, we've already seen that with other examples, so I won't cover it. And we've got the fitted example as well. And again, as we saw previously, if I just refresh the views, if we look at the fitted data, it's basically taken all our source data and fitted it to the curve. And in my view, I've created a column called life spend underscore fitted, which shows that fitted value. Which means if we want to have a look at what that curve's like, we can actually do that just by plotting this out. We can plot life spend, we can plot income, and then life spend fitted on our response axis. And now we can see basically what that curve is looking like. So it's looking like a natural logarithmic curve, and we see the data are actually source data fitted to it. So that's what we do in terms of evaluating our model and creating it. Then the next thing is simply to actually start using it to predict information. And here's the code for that. It's the same code basically that we've already seen. The only difference really is that we have a different value here as a third parameter to the wrapper generator. We have forecast with LNR for logarithmic natural regression. So forecast with LNR this time. Otherwise, it's basically the same. And in fact, under the covers, what's happening as that model's built is that the PAL is actually converting using logs to take the natural logarithmic values and to create something linear, doing the regression on that, and then converting the results back again. So it's doing lots of interesting stuff under the covers for us. So if we're to run that, we can create that algorithm and run it. What might be interesting, just to show you, and you could do this for any regression, if you wanted to really just chart out that curve that's been fit to your data, then you can actually just create maybe a table with a set of values here just from 1 to 10, And we've got an index and a value of income from 1 to 10. And then you can actually have it set the values, basically predict or forecast the value of lifetime spend for each one of those, meaning that you can just get a good view of the curve that's been created. So if we just run that code, okay, it's run very quickly, no problems, could be running on a large volume of data. So if we want to look at the values that we have created, we can go to that predicted table and we can perform a preview. And we see the fitted values, and what we can simply do is chart that. So if we were to chart the fitted by ID, maybe make a line, now we can see across the values of our ID, our income values, we can see we've got what the natural log curve looks like. So it allows us just to get a view of that curve should we want to do that. However, what's ultimately more interesting is that we might want instead, let's just remove that standard example there and go to a real prediction where we want to look at another two. It's the same we've done in the other examples and predict some new values. We can run this runtime part again. So we clear out the tables, truncate table for the input data and the output. We run the algorithm on our model with that new input data. And now if we go to our predicted view, we're able to see not only the original source information, the 150 customers, but also the two new ones with the predicted lifetime spend values. And of course, if we're to chart that, what we can then see is we've got our two new values. And in the case of this natural logarithmic regression, the actual values for life spend are not the same as they were, for example, when we were using linear regression or when we were using geometric regression. So those are our two predicted values seen in the context of the rest of the data set.